My name is Tabitha Chebet, and I'm going to be taking you through a project that I worked on with my teammates. It's entitled Graph Reasoning Large Language Models for Inclusive Home-Based Mathematics Education in Uganda. So caregivers and parents often find themselves in a position in which they lack the tools to provide Uganda curriculum-aligned support to their learners at home. Besides this, children often struggle with mathematics, and this is even more pronounced for students with learning disabilities. Digital learning tools that exist today are not aligned with the Uganda national curriculum, which also makes it, which further goes on to show the issue that's currently existing. So the goal that we have from this is to support parents, or to provide a tool that will be able to support parents and teachers so they'll be able to provide the support that their learners need and help them through their education journey. It's meant to be adaptive and also to provide inclusive math learning with a specific focus on students, primary school students with learning disabilities. It's also meant to be a tool that is generating content aligned with the Uganda national curriculum. So for the literature review, we went through a few papers in order to understand more of the project and to also prepare more. One of them being Attention is All You Need, a paper in which the novel transformer-based architecture was introduced. This is an architecture on which all the models we trained are based on. Besides this, we also read a paper entitled The Modeling Relational Data with Graph Relational Networks. This is a paper that introduced the RGCNs, or the RGCN encoders. RGCN stands for Relational Graph Relational Networks. These are neural networks that are able to encode the relationships between multi-edge graphs. This was very key in our project because the RGCN was trained on knowledge graphs from our dataset in order to produce embeddings that we use to fine-tune our models. We also went through another paper called Analyzing AI-Based Educational Platforms for Supporting Personalized Education, Personalized Mathematics Learning. In this paper, a number of platforms, AI-based educational platforms such as Khan Academy, were analyzed, and it was noted that these platforms do not offer flexibility in terms of presentation format. Besides this, they also not aligned with the Uganda national curriculum, which is a key gap that we hope to solve using our tool. So, caregivers and parents do lack structured curriculum-aligned guidance to support their learners, most especially in a home-based learning environment. And this becomes more difficult for parents of learners, of students with learning disabilities, because they are not sure or certain of how exactly they should help their children pick up these concepts faster. This goes on to highlight the inclusive educational gap that is currently existing. So the AI tool that we come up to solve this problem must generate lesson plans, examples, and exercises tailored to specific learners. It should also be inclusive and should adapt each task for diverse cognitive and sensory abilities. It should also be able to work online so that it can be deployed in resource-constrained environments. So these are some of the research questions we have. How can home-based caregivers support math learning effectively? How can AI generate adaptive aligned, curriculum aligned content? Some of the objectives we got from these questions were to develop an AI-powered coaching tool and to generate adaptive, inclusive, curriculum aligned math content. So from this, we were able to create a data set for our project. We also built an intelligence system that acts as a coaching tool for mathematics, specifically for students with learning disabilities. We also developed the first LLM-powered co-teaching tool aligned with Uganda's NCDC primary mathematics curriculum. The methodology we used employed graph dataset creation, knowledge graph construction, encoder training, fine-tuning reasoning, deployment, and validation and feedback. During dataset creation, we used resources from the internet, resources from the NCDC, NCDC-based websites, resources from disability-related websites, extracted this information using Google Notebook LLM and structured this into a tabular dataset. We passed this tabular dataset in a knowledge database and converted it into knowledge graphs. These knowledge graphs served as input for our next phase, which is encoder training. They were used to train the RGCN encoder and produce embeddings that we used to fine-tune the model. So during fine-tuning, we were doing training and validation and testing of the model to provide the kind of output we needed at inference. Once all this was done, we deployed the model in Hugging Face spaces, and we are currently waiting to do validation and feedback. For the model architectures, we trained about 3 models. We trained 3 models: Llama 2B 7 chat, Llama 2B IT, and Falcon 3 1B instruct. Now, all these models are based on a decoder-only transformer architecture, with the major difference being in the way they operate internally, but also in the positioning, the most notable difference being in the positioning of their normalization layers. Llama 27B has pre-normalization. This is where the normalization layers come before the transformer sublayers. While Llama 22B IT has a hybrid, a combination of both post and pre. As for Falcon 3.1b, we weren't able to find publicly published resources on the internet that would help us clarify on where its position or what the positioning of its normalization layer was. So these models, what happens is that when a prompt is entered into any of these models, the prompt or the input is broken into tokens, and these tokens are attached using a tokenizer, and these tokens are assigned token IDs. These token IDs are now placed in a tensor IT that you can see here. This tensor is mapped onto a vector space E. So during this mapping, the result of this mapping is the token embedding matrix, which is the next input for the self-attention layer. In the self-attention layer, this matrix is mapped on to 3 vectors: the key, the query, and the value. We're going to see their use in the incoming slides. So what happens is that the model does not know how to order these tokens. It doesn't know how to order tokens. So what happens is that we apply positional encoding, and all 3 models apply rotary positional encoding. This is where we inject the keys and queries from the previous step with information about their relative position. Once rotary positional encoding is done, we move on to the attention calculation. In the attention calculation, our softmax function is applied to these operations in order to convert the output we have from this into attention probabilities or attention weights. These attention weights are going to be multiplied by our value vector in order to come up with a weighted value sum. This is going to serve as a matrix input for our next layer. The graph, all the 3 models employ graph query attention. Graph query attention is a generalization of MHA. MHA is multi-head attention. The difference between the two is the fact that in GQA, we have a group of heads sharing the same key and value vectors, which makes it more efficient when compared to MHA. We have normalization applied to our matrix. Normalization, the purpose of normalization is to rescale the embeddings for each token in order to promote stability during training, and all models apply the root mean square normalization. We also have used residual connections applied in each of the model architectures in order to mitigate the issue of vanishing gradients during back propagation. So this is basically where we add the output to the input, and then that serves as input to the next layer. It also helps us to have different layers stacked on top of each other and have deeper layers in our decoder model. So when you look at the feed-forward neural networks, we have Swiglu and Geglu. Geglu is employed by Llama 22BIT, while Swiglu is applied by the Falcon and the Llama model. The use of the feed-forward network is basically to enhance expressivity of the model. It's supposed to allow the models to capture more complex relationships between tokens. So those functions applied to the matrix that we have, and then it's passed on to the layers that follow. So by the time it reaches the linear layer, it has passed to the final layer. Now, this linear layer is going to convert that output matrix that we have from the final layer into logits. Logits are raw scores. These raw scores are going to be converted by our softmax function into probabilities that are going to serve as that the model can now use to make predictions. When you look at our dataset description and exploratory analysis, the dataset we developed was to serve the purpose of providing a basis for generation of NCDC aligned mathematics content. The data collection method involved extracting papers and manuals from the internet, from NCDC-based websites and disability-related websites as well. We use a Google Notebook LLM to do this. We structured it into a tabular dataset with 13 columns and later on cleaned and standardized it to remove formatting inconsistencies. When you have a look at our tabular data analysis, you can see that there's relatively uniform distribution of the classes, meaning that there's going to be fair representation across all primary levels in the generated output. When you look at the disabilities per class, you can see that there's sparsity because some of these disabilities are not well represented at all for any class. And that means that there's going to be a high potential for catastrophic forgetting because of their poor representation in the data set. When you look at the next two graphs that we have, you can see that there's an imbalance between the most represented class and the lowest represented class. This means that the model is going to be biased during generation of content, and it's not going to be able to generalize as well for the lower represented classes when compared to the most represented classes. When you look at the node degree distribution, you can see again that majority of nodes have low connectivity, which actually goes on to fit into what the results we have from the heat map. A minority of them do act as hubs, actually central for the model learning relationships between the different nodes that exist in our graph. Again, you can see here that there is a disparity between the most represented class and the lowest represented class. And this means that there's going to be a bias. There's a large likelihood of our model being biased when generating content. It's a similar thing for the distribution of edge types and knowledge graphs, though it's more evenly distributed for the first few classes when compared to the previous bar graph. So after training and validating, we tested these models. From the three models, we were able to observe that the Gamma and Falcon model had better loss, perplexity, and BAT scores when compared to the Llama model, which had better Roche and BLEU scores. The better loss and perplexity scores for Gamma and Falcon means that they successfully converged, or they converged better during training when compared to Falcon 27B. When you look at their BAT scores, their higher BAT scores when compared to Llama, we are able to see that the semantic similarity of the text that they predicted was higher when compared to the actual text. When you look at Llama and its high BLU score, we can deduce from this that the Llama model, the generated text or the predicted text for the Llama model had better or closer textual similarity when compared to the actual text. Now, we conducted XAI we did explainability in order to promote transparency and also understand how our models reason to produce when producing the output they do. When you look at the Falcon 3.1b instructor model, this is particularly for the last layer, layer 17, we can see that the upper right side of the diagonal is black. This goes to show us the application of the causal mask, which is a key feature in autoregressive models that prevents them from seeing feature tokens. When you look at the diagonal line, it informs us that the context of the next token is being formed by that of the preceding token. In other words, in order to predict what's coming next, we look at what's back. When you also look at the lower left side of this graph, you can tell that the model was able to recognize longer range dependencies between different tokens. And this is majorly to do with the fact that this is also layer 17, meaning that this is basically a combination of all the relationships and all the patterns that have been recognized in the other layers now coming to the final layer. So because of that, it has more, let's say, knowledge of the dependencies or the relationships between different tokens when compared to the first layers, like we shall see in the next slide. When you look at the attention heat map for Gamma 22B, we can say that this is attention heat map for the first layer. And usually in layer 1, the model does not have as much context. It is basically the attention it gives to the tokens is usually highly localized. It's usually looking at the nodes that surround the token, and it's not usually looking at the longer range dependencies that it's yet to learn. So when you look at the hidden set gradients, we are able to see what the models are paying more attention to. What Falcon and Game are paying more attention to is basically the very first token, which is the question token which. When you look at mathematics and student, those are in blue. That means that these did not contribute as much to the output or to whatever was generated in response to this prompt. When you look at Llama, however, we can see that mathematics, early important, played a bigger role in informing the generated output for this prompt, even as compared to tokens like Y. Some of the limitations we faced were limited access to significant computational power and memory sources. This is majorly on the platforms that we use, such as Cargo and Colab. We often found ourselves running out of GPU resources. Besides this, we also faced a challenge or during collection of data, it was a bit challenging for us to find curriculum-aligned content that was learning disability specific. Besides that, the models also took quite a while to train, which also limited the number of configurations or the number of adjustments we could make to them in the time that we had. So to solve these, we used LoRa to reduce the trainable parameters, and we also reduced the testing and training batch size to prevent out-of-memory errors. During deployment, or for deployment, we selected the Falcon 3.1b model. And this deployment was basically majorly based on the experimental results we received because we haven't done validation. Falcon 3.1b had better overall scores in relation to all the models that we trained. But besides this, it also produced better output at inference and took less time to train. When we were deploying it, we deployed it on Hugging Face spaces. We basically got the LoRa adapter files and packaged them with an upload.py file plus other files, the upload.py file with other files like the requirements of text file. We uploaded this to Hugging Face spaces. That also gave us the Gradio app that we used to design the interactive environment or the interactive web-based environment for this application. So major components consist of the front end, the back end, and the model. The front end consisting of the Gradio interface, the back end consisting of the transformers, and the model being Falcon 3.1b that executes inputs. When we look at the flow of use, it's very simple. The user simply puts in the prompt they want. The model processes it basing on what it learned and then produces the output, which is what a textual response. The IP assets we have are knowledge graphs, linking concepts, and the fine-tuned large language model that we trained. So we successfully developed and fine-tuned lightweight LLMs using curriculum-aligned graph data, demonstrating practical potential in AI-assisted learning and curriculum analysis. For the future, we plan on enhancing the model performance by fine-tuning it with more advanced models. We also plan on moving to a site that will allow us to scale more, so that in case we have more users, we will be able to accommodate them. We also plan on evaluating it with educators so that we can know what we need to change and fine-tune, and optimizing it for deployment. We also plan on using knowledge distillation so that the application will be available for users in low resource environments. So we'd like to acknowledge our supervisor, Dr. Galiwango Marvin, for his guidance and feedback. I'd like to acknowledge the School of Education, Macquarie University, for the help that they provided us toward the course of this project. I would like to recognize my team members for their collaboration and open source communities such as Hugging Face and PyTorch for their tools. Thank you.